cones have a better ability of producing discrete images or discrete points between, or discrete distances between points, because each little cone provides its own signal. All right? Whereas a rod provides multiple signals. All right? So you lose that resolution. Okay. What's the other one? Now, ganglia cells are boring. We're not going to really talk about these a whole lot. But basically, you might hear a neural ganglia when you get in the lab some and talk about ganglia. Ganglia are just regions. So the ganglia region is just an accumulation of multipolar neuron cell bodies. Axons. And these are the afferent neurons that collectively, so we're going to circle them all collectively, are going to help form the optic nerve, which actually carries this vision information you're receiving back to that occipital primary vision center, vision processing center in your brain. So they're pretty boring. They're just typical multipolar neurons. So basically, just from structural makeup, we can kind of get an idea how the retina is going to work and how it's actually going to be able to convert physical signals into a chemical signal. Take that to the brain. Rods and cones are actually going to do the light converting into the chemical signal, and they're just going to pass that signal on to these bipolar cells. Now remember, only receptor potentials occur in these separate cells. So you're going to have receptor potentials here. Whereas here, in these two types, you can produce action potentials. So basically, as soon as enough light hits these retina, or these photoreceptors, that a signal can be processed or sent to one of these bipolar cells, at that point, an action potential can be generated. And we know that action potentials are all or none events. So as soon as an action potential is produced in a bipolar cell, you will get a light transmission, or a transmission of what that light was bringing you in terms of your vision to your brain, where that signal can be processed and produce an image in your head. So you can perceive something that you're seeing. So pretty simple stuff so far, right? All right, let's talk a little bit more about the retina here. Go back to our big image. Because all the little axons, so we'll call this axons of ganglia. So the axons of our ganglia layer, all those axons travel to one discrete point in the eyeball. At that point, we call this your blind spot. Because at that blind spot, you don't have any photoreceptors. This is the point at which all those axons actually converge and push through the choroid and the sclera. These axons then carry the signal to your brain. This is the optic nerve. So the optic nerve originates from that blind spot, right? That's pretty good eye anatomy so far. Let's see. What else do we want to talk about here for eye anatomy? Retina pretty good so far? Any questions so far about the retina? Again, we're going to get into more detail on the retina here in a bit. All right, well, let's move to the lens. Let's talk about lenses a little bit, because lenses are important, and they're a little confusing, so we should talk about it. This board is like completely opposite of intuitive. You'd think it'd be easier to pull down than push up, but it's exactly the opposite. It goes against gravity. Newton would be proud. Did anyone did gravity? lenses are very confusing, and we're only going to talk about them in terms of what you need to know to understand how the eye works. Because you could spend, I don't know, when I teach microscopy courses, sometimes we spend 2 weeks on them because they can be very confusing, especially when you have multi-lens systems like the eye. But in general, the function of a lens is to refract light to a discrete focal point on the retina. All right? Focus light at a discrete point on the retina. So what is refraction? Refraction Refraction is basically the bending of light when light travels through a medium of different density. All right? And what's kind of neat is all light wavelengths bend slightly different depending on the density of light of the media they bend through. So if you think about a diamond, you see nice sparkly colors of all wavelengths of light because each individual wavelength will bend to a different degree. We're not really going to talk about that much because that gets into even more complex lens properties. But refraction, that's the key thing, you should know that. The lens basically is refracting light to your retina because the lens is actually going to be a higher density media than air. So when light's traveling through air, so in your environment, when it hits your lens, it's going to bend. So it's not going to be traveling along the same pathway anymore. Because light rays travel in straight lines. Now there's light waves traveling in all sorts of different straight lines. Each individual light wave travels in a straight line. But when it hits a medium of a different density, it will bend. And the degree of bending can be altered even greater or lesser depending on the curvature of that higher density medium. So not only are lenses have higher density media, they also have curvature to them that allows light to even refract more. Right? So your lens is responsible for refracting light to your retina, but also it's responsible for something else that we call accommodation. I can give you a pretty mammalian type definition for accommodation because we're not really going to talk about other organisms in this class. Accommodation is basically the ability of a lens to change the amount of refraction that can occur when light travels through it. And your lens does this by changing shape. So not only is your lens important in refracting light to the retina, it's important in changing shape so that it can alter the degree that light is refracted. That's called accommodation, basically altering the degree to which a light wave is refracted as light passes through the lens. Like I said earlier, other organisms are different because instead of changing shape, they'll move that lens back and forth. But for us, we just change the lens shape, and we do that through functioning the ciliary muscles. So, let's think a little bit about how lenses work. So there's multiple types of lenses, and usually when we talk about lenses, we talk about a convex lens and a concave lens. They give us the best examples of kind of what you should need to know. So convex lens. Convex lens is like our lens, right? So no caved sides, that would be a concave lens. Or a concave lens is cavitated. Right? So, how do these lenses differ? Convex lenses are often called converging lenses. Converging lenses. Whereas concave lenses are often called diverging lenses. And basically, a converging lens is going to converge light. It's converging light to a one point, right? To a single focal point. And that's what we want. The lens is supposed to be functioning to provide a single focal point on a retina. Basically that means, well, let's use a good color for light. Purple, that's like light, right? Basically this means, as parallel light waves, we'll draw a few parallel light waves. As parallel light waves hit a converging lens, or this convex lens, they're going to converge to a single point. And they do this because as light passes through this denser medium, it slows and it bends, especially at the greater curvature of the lens. And if you look at a lens, where's the greater curvature going to be? The greatest curvature is at the periphery. So you actually get very little bending of light at the central portion. But at these greater curved portions of a converging lens, light waves bend and then bend again as they feed back up and pass through that medium. So what you get is light converge to one point. Make sense? Diverging lenses work exactly the opposite. Pretty similar in the central portion where you don't have much curvature to the lens, but at these external portions, light waves actually will bend and diverge away from a common point, right? Now, the problem with lenses, though, is that this is not stereotypical of how light hits your eye. Because as you know, we have the sun, light waves coming down in basically one direction from the sun, but you perceive different images from light waves bouncing off of different objects. There's objects all around you. So you don't have parallel light waves hitting your eye when you're trying to see an image. So you have light waves coming from all sorts of different directions. So this complicates things a little bit because we don't have this nice normal parallel light hitting the lens of our eye, which is what the cornea is for. The cornea helps bend light to a parallel pathway before it hits your lens. And we'll talk about that in detail when we get to kind of the overall how your eyeball works. But in general, your lens is this type of lens, a converging lens, because converging lens converge light to a single point. So you want to converge light to the retina so that you can stimulate photoreceptors, and then they can carry those signals, those physical signals that you turn into chemical signals, to that occipital lobe of your primary visual center. Does that make sense? So lenses aren't that bad. Now, let's see here. Let's change, erase this. I'll show you why lenses have to change shape. So if you're looking off in the distance, way out way, if you did the photography, you would call this infinity focus. If you're looking way off into the distance and focusing on a central point, a lot of the light coming from that area is going to be hitting your eyeball from that way off distance in parallel rays and gives you something like this. So you should have vision. However, if you're trying to focus on an object and it's coming closer to you, an object starts coming closer to you, what happens to those wavelengths?